All right, hello, what's going on? It's your boy. So today we'll be going over a really interesting integration technique, which is known as U-substitution. And U-substitution exists because there's no real quotient rule or product rule when integrating or finding the integral of a product or quotient. So U-substitution works by making a substitution and then simplifying the inside integrand to a point where then that kind of substituted equation or substituted kind of statement is integratable, if that's a verb. But instead of talking about it, we'll do a couple of examples to try and break this concept in, I guess. And yeah. So with U-substitution, we assign some part of the integrand to be U. Typically, U is always going to be the statement, when it's, of course, when we're dealing with polynomials, it's always going to be the statement or part of the integrand which is of a higher order. And we can see automatically that this higher order statement would then, in this case, be x squared minus 1. So that's our first step, assigning U. The second step is to then differentiate U. And sorry, in this question, it should be with respect to x. So when we do du, and we take the derivative of du, the Leibniz notation of that would be du by dx. And if we take the derivative, it then becomes 2x. Now, from here, we want to isolate for dx, so we can make a substitution for dx in terms of u, in terms of du and x. So if we do a little algebra, we find that dx is equal to du over 2x. So we've done the main two things, and so all we have to do now is substitute our new values. So it then becomes, this whole thing then becomes x over u, which is now x squared minus 1, so we have u, and then we have du by 2x. Quite conveniently now, we just want everything in u, in terms of u, and these x's cancel out. We then have that, if we factor out the 1/2, we have that 1/2 times the integral of 1 over u. Now notice, 1 over u is actually integratable. It's just the natural logarithm. So you see that this entire thing here, which we didn't really identify to be integratable, is now this integratable thing that is much easier to work with. So now we have, if we evaluate 1 over u, the integral of that is just 1/2 times ln absolute value u. I mean, the absolute value isn't too necessary if your u is positive, but I'm just going to put it in there. And remember, we just integrated, so remember your plus c. You always need your plus c even immediately after you integrate. It's going to have to be there in all the steps. So if we have that 1/2 ln absolute value, we just substitute u back in as x squared minus 1. That was our original substitution. So now we have that u is equal to x squared plus 1 plus c, and that's your answer. That's how you do this first question. So I hope the steps were a bit clear there, and we're going to cover a lot more ground with this, so we can kind of get used to harder examples. Let's do the second one. So first, we find what u is, and the higher order statement in this case is the denominator. So that's what we're going to set u equal to. Our second step is to then find the derivative. And of course, we put it in Leibniz notation because that's how it's most easiest to interpret. So with this, we have 2x plus 2. Then we isolate for dx. So we have dx is equal to du 2x plus 2. Then as we did in our last example, we just substitute in these values. So we have the integral of x plus 1 over u, right? And then we have dx is now equal to du over 2x plus 2. And right off the bat, it might be a bit hard to see. You might think, well, hold on, these two things, x plus 1 divided by 2x plus 2, that doesn't cancel out, but it really does. And all you have to do is a bit of algebra. So you have x plus 1 over u times du. All you got to do here is factor out the 2. And now we have two terms that cancel out. And then, again, this becomes really self-explanatory. Factor out a 1/2. We have 1 over u with respect to u. Again, this is just the logarithm, the natural logarithm identity. It's just integrating 1 over u. And so when we do that, we have 1 over u, 1 over u integrates to ln u. So we have 1/2 times ln absolute u plus c. And our final answer then becomes 1/2 ln of absolutes x squared plus 2x plus 1 plus c. And that's our final answer. So again, I hope you're seeing the pattern we're kind of doing here. We're trying to get rid of our x terms by canceling them out, and we're trying to have everything in terms of u so that we can very simply integrate what we have with respect to u, and then in our final step we just resubstitute. So let's do this question. This question is a bit of a tricky one, I think, but it's one that's very doable. So it might not seem like we have a product or a quotient because it's just tan x, but we know that tan x is just sine x over cos x. So that's exactly how we're going to write this one down. So in our minds, we might not know right away, well, which one do we call u? But if we think about it a bit harder, we know that the u term is going to be differentiated, and then we're going to take that differentiated u term and divide. So if we take u to be sine x, let's just do a bit of trial and error here. Du by dx will equal cos x. And so dx will equal du over cos x. And then our final integral will be it will be u over cos x times du over cos x. And these two will not cancel out. So this u must not be u must not be able to be sine x. It must be cos x. So let's see what happens with cos x. With cos x, du by dx is negative sine x. And so dx is equal to negative du over sine x. And then we make a simple substitution. So our new integral becomes sine x over cos x, which we assign to be u, times dx, which we now call negative du over sine x. And when you look at that, the sine x's quite conveniently cancel out. So what we're now left with, if we integrate this, if we factor this negative out, we get 1 over u by du. And we already know that the integral of 1 over u is just the natural logarithm of u. So negative ln absolute u plus c. And the final step is really easy. We just plug in back for u. Cos x plus c. And that's how you do it. So these were a bit of beginner problems, and we're gonna jump to some more intermediate ones right over here. So this whole hairy thing right here, this question 4, looks daunting, but it really isn't. So again, we call u to be the higher order term, and in this case we have 6x minus 1, and we have 3x squared minus x. Now right off the bat, 3x squared minus x is the higher order statement. It's raised to the second power, while 6x minus 1 is only really raised to the first power, right? 6x to the 1, 3x to the 2. And so we're going to call u 3x squared minus x. Then we, of course, take the derivative, and we get that this is 6x minus 1. And right off the bat, you'll see that this will cancel out quite nicely because we have two 6x minus 1 terms, and we're going to be dividing by 6x minus 1. So if we work that out, we have dx is equal to du over 6x minus 1. And now we just do the simple substitutions. I'm actually going to just factor this 3 out because it's part of the product, so it's factorable. And then we have that 6x minus 1 e to the u is equal to du over 6x minus 1, right? We substituted this power right here for u. We substituted this for du over 6x minus 1. And so if we work this out, of course, these two things cancel out, and we're just really left with eu du. And we know that the integral of eu is eu because the derivative of eu is also eu. So we have that 3eu plus c is our integral, is our new answer, but we have to substitute back for u. So we have that 3e to the 3x squared minus x plus c is our answer. Oh, sorry, minus x. So this is our answer. And this just brings up a good point. Even when you see really kind of long and maybe disturbing questions, just kind of carry through with the regular principle of identifying a u, and making sure that that your end integrand is only in terms of u so that you can properly integrate it. All right, this question right here is a bit misleading because if you look really closely, we might call this or this u because they're both raised to the same power. This is a problem because if they're raised to the same power, then by the derivative, things won't cancel out. X's won't cancel out. And that's a problem because we really need x's to cancel. We need our final integrand to only be in terms of u. And if x's don't cancel out, then we'll have x's and u's, which in that case is not integratable. So what do we do? So when you see the same power, you're going to call u the more complex term. X plus 1 is more complex than x because there's an additional plus 1 term. Then we carry out with simply taking the derivative of u, which is just going to be 1. And so if we isolate for dx, we see that dx is just equal to du. So let's do a bit of substitution here. We have that x root u is then equal to just du. But see, this is a problem because there's still an x. So how do we get rid of that x? Well, we know that u is equal to x plus 1, so x must be equal to u minus 1. So x plus 1 equals u. Therefore, u minus 1 equals x. So we've now written both x terms in terms of u. So our new integral becomes the integral of u minus 1 times square root u with respect to u. And you can actually just expand this. We have u minus 1 equals u to the 1/2 du. And it really just becomes exponent rules at this point. If we multiply u and u 1/2, we get u 3/2 because we just add the exponents. 1 plus 1/2 is 3/2 minus u to the 1/2 du. This is now something we can definitely integrate. The integral of u to the 3/2 is u to the 5/2 over 5/2 minus u to the 1/2, which we just add 1 to, so u to the 3/2 divide by 3/2 plus c. Now, if we divide by a fraction, we multiply by its reciprocal. So we have that 2 over 5 is equal to u 5/2, but now we're going to start resubstituting for u. We originally called u x plus 1, so anything that's u is also x plus 1. Minus 2 over 3, x plus 1 to the 3/2, plus c. And that's our answer. So that was a bit of a tougher one there, but I'm sure you guys could handle it. This last one here is also misleading. Notice, we don't have the only x term we really have is this, right? So we can call this u for sure. But when we take the derivative will also just have an x in it. The 2x will reduce to an x, but that's a problem because x won't cancel out with anything. We have a 1 as the numerator. So in this case, we have a bit of a similar situation where the x's don't cancel out and we need something to do about that. So in this case, I'm not going to make a u substitution. I'm going to make an x substitution. So instead of saying u is equal to 1 minus x squared, I'm going to say x is equal to sine u. And you'll see why I signed x to be sine u in just a second. So if we take the integral, we have that 1 divided by 1 over x, divided by the square root of 1 minus x squared becomes 1 minus sine squared u. Now, before I continue, we need to make sure we actually take the derivative of dx with respect to u. So dx with respect to u is just going to be cos u. And, of course, we need to isolate for dx, so we have dx is equal to cos u times du. So I'm going to make that substitution for dx. 1 minus sine squared u is equal to cos u du. Now, why did I pick sine u out of all things to be x? Well, that's because when you take x squared and, of course, plug in sine u, you get sine squared u. But notice, this is a very well-known identity. It is, by the Pythagoras identity, just going to be cos squared u, right? Because cos squared u plus sine squared u is equal to 1, and this isolated is just this minus this. So, oh, sorry, the other way around. So cos squared u is equal to this minus this, and so this is equal to this. So really what we have here is the integral of 1 over root cos squared u du cos u. Now, the square root of cos squared u is just 1 over cos u. So we have 1 over cos u du cos u. Now, would you look at that? The cos's very conveniently cancel out. So we have that 1, the integral of 1 du. If we take the integral of 1, then that just becomes u. And that's because we're integrating with respect to u. So then this just becomes u plus c. But what is u? We know for sure that x equals sine u, but we don't really know what u is. U is just the arcsine x. Because if we want to isolate for u, we have to take the arcsine of u so that it goes to the other side. So our final answer is arcsine x plus c. Fear not, however, you don't really have to do all of this on a test or exam, because this formula is actually in your formula booklet. And there are a lot of other trigonometric functions and integrals that are found in your booklet. So it'll save you a lot of time in the test. More often than not, you'll just have to manipulate algebraically and factor out a few things to get an integral to look like this. And then you can just automatically convert it to arcsine x with the factors that are now multiplying this integral. But we can save that for another video because it's not too important. I hope this was a bit helpful, and if there are still any questions out there, feel free to ask them. Alright, peace out.